We have proved that a language is accepted by epsilon NFA if and only if it is accepted by some NFA, if and only if it is accepted by some DFA. So we have proved the equivalence of these three models, this epsilon NFA, NFA without epsilon transition, and DFA, right? So if a language is accepted by any of this model, then we call that language regular. Okay, so a language is regular if it is accepted by any one of this finite automata. It's equivalent, right? All these conditions are equivalent. It does not matter which type of finite automata we are saying. We can just now say that finite automata. Okay. Now, in this lecture, we are going to introduce another formalism. It is not a machine, but it's more like a shorthand notation to express a language. So that is called regular expression. Okay, a regular expression. And we will see that this regular expression is again equivalent to this model. So all four of them will be equivalent. Now, in order to do this, it's helpful if we first prove some closure property of regular languages, right? So again, by regular language, we mean that anything which is accepted by any one of this model. So we will prove these two theorems that if L1 and L2 are regular languages, then that will imply that their union and concatenation are regular. Okay, and similarly, if L is regular, then its clean closure is also regular. So on the very first day, I defined this concatenation of language and clean closure of language. So what was that definition? So it was this. So the concatenation and clean closure doesn't require you to start with regular language, right? You can take any language and take their concatenation and clean closure. So what was the concatenation? So if you take any two language, L1 and L2, so then you take this sort of string, which is concatenation of some x and y, where this x is coming from L1 and y is coming from L2. So you take all such strings which you obtain by concatenating some string in L1 and some string in L2. So that set is denoted as L1, L2, and this is the concatenation of the language, right? So this is the concatenation of string and this is the concatenation of language. So again, some example I gave earlier. So if this is just say A and B, so and this is C and D, so then you will see that this is just this all combination of this thing. So I could have some string with length larger than 1 here, and if I take this to be say this A star, so again what was A star, epsilon A square, A3, everything, and here again all strings constructed from B. So then their concatenation is just AI concatenated with Bj for all ij, right? All natural number ij, including 0. And what was clean closure? So we defined for any language L, okay, for any L, even if this is empty, we define its 0th power to be just this set containing the empty string, and then this Li is just L concatenated I many times, right? So we can recursively write it like this. They are equivalent. So yeah. So in other words, this Li is just concatenation of say x1 up to xi, where each of this xj's are coming from this L, right? So we can write it like this: for I greater than 0, for I equal to 0, we define it like this. And then clean closure is what? So this is the union of everything, all the Li's, right? So that is the clean closure of L. So we did that in the first class. It's just a recap. So depending on the definition, now we are going to show that for any two regular languages, their union and concatenation are regular, and for any regular language, its clean closure is also regular. So let's begin with that union thing. Now, first you notice that if you have a finite automata for a regular language, okay, so any finite automata, and you have a set of final states, you can have multiple final states, so then you can construct another finite automata like this. So you take all this final state and you attach this epsilon transitions to some new state. So this is one new state that you are introducing. You are, I mean, changing the set of state by just adding one more new state, and from all final state of this given automata you now do this add this epsilon transition, and in this new automata these are no longer final state, right? So these are no longer final state, you only have this one final state. So you can easily see that these two finite automatas are equivalent. Why? Because so when is, say, W accepted here? So if you have some path through some state which ends up in some final state, right? So the label, if you concatenate all the symbols, so you should get this W, right? And if you have it here, then you can also you have the same path here, the same thing here, and then for this you can now take this epsilon transition and then reach this newly constructed state. So it is also accepted here, right? On the other direction, if you are accepting something here, so that means, say, on some W here, you need to start from here and you need to reach this state because this is the only final state. So that means the last transition has to be one of this transition, right? Because from here there is no outgoing edge. So if you are accepting W, that means if you are reaching this state by processing W, then the last transition has to be one of this transition. So that means the state before doing this it was one of this state, right? So that means here in this part you reached from here to one of this state, and so that means this W is completely processed during this part, and that means here also you can have that path, and that means here also it is accepted. So these two are equivalent, right? So what I'm saying is that so what I'm saying is that from here to here, I mean, if you have any string which is accepted here, then it has to come to one of this final state and then take this thing. So now if you just consider from here to here, you can have the same path here. So that means here also you are accepting that W. So we will draw this as a black box sort of figure. So we have a unique starting state, and now we also have a unique final state. So it has just one final state. Okay. So for any given finite automata, we can transform it in this form. So now with this, let us first prove that union of regular languages is also regular. So suppose we are given this to regular language L1 and L2. So that means we have a finite automata, say M1 and M2, which accept L1 and L2, right? So now we construct a new automata. So this is a epsilon NFA, right? So how do we construct? So we are introducing two new state, right? And here this is the unique final state, this is the unique final state. Uh, and here they are not final states. So here this is the unique final state, and this new state is the starting state. From here we have this epsilon transition, here also we have this epsilon transition. Now you see, again, it's immediately clear from this picture. So when is, say, some w is in this language, so if it is either in L1 or it is in L2, right, either this or this. So if this is the case, so if this is in L1, so then this is also accepted here, right, because that means there is a path from here to here with w, because there has to be a path from here to here on w, right. And now you can also consider this to epsilon transition before reaching there, and then this. So w is accepted here. Similarly, if w is in L2, so it will be accepted via this route. Okay. So in this case, so L1 union L2 is a subset of say this thing. So one direction is proved, but this is if and only if you can see, because so we showed that something is here means it is here, but if something is here, that means if some w is here, so that means there should be a path labeled by w which starts from here and reaches here. So how can it reach from here to here? It has to first take one of these two transitions, right? So suppose it takes this transition, so there is no way to go back now, right? So only way it can process this w is that it has to go forward and exit through this state, right? And if it does that, then you can see that this w is entirely processed within this part. So that means this w is in L1, and the other possibility is that it can first take this and then do this and then go there. So in that case w will be in L2. So you see that L of m is contained in L1 and L2. So either way, so first we proved that this is contained here, and then we proved that this is contained here. So they are equal, right? And concatenation is even easier. Again, we have automata for L1 and L2, like the previous slide, M1 and M2. And then we construct this automata, right? So from this F1 we make a new transition, epsilon transition, to this starting state here. This is no longer a final state in our machine. So this is the final state and this is the starting state. So again, you can see that you can reach from here to here if and only if it is of the form that you have some x here and you have some y here, and in between you have epsilon. So that means together it's just xy, where this x is coming from L1 and y is coming from L2. So sorry, this is a typo. This is a typo. So this should be L1, L2. This should be L1, L2. So just take a note of that. There's a typo here. So there's a automata for accepting this concatenation. Okay. So now this is a typo again. So this should be L star. So now see this, I again claim that this is automata to accept L star, where this M is accepting say L. Okay, and why is it so? Because you see, when will it be in L star? So W is in L star if and only if this W is some x1, x2 up to some say xi or some I, right? Or W can be epsilon also. So one of these two possibilities. And you see that epsilon is accepted by this thing, because you can take this this edge. So epsilon is in the language of this M prime. Otherwise, what can happen if you do not take this route? Then you have to take this route. Okay. So then from here, the only way forward is again through this this machine, right? So if you reach here, that means you have already processed some x1, where this x1 is coming from. So this x1 is coming from L, right? And then you can either take this way out to the final state. If you do not do this, then the only way out is to take this. So you may say that there can be some back edge through this machine, so that's fine. So you come here and then again go back and then do something, but then again you have to come back to this point in order to exit, right? So this entire thing that you are doing inside this blue box, so that I call as say x1. Okay. So then yeah, at some point of time after doing this x1, either you take this edge or you take this edge. So this is a epsilon, so it doesn't contribute to any input symbol. So then again you do this, and that I'll call x2. So x2 will also be in L1, and similarly you can take this edge multiple time and do this x1, x2, x3, and finally you take this exit and go to the final state. So you have accepted something of this form, where each of these xj's are in L. So this is the machine for L star. Okay. So after proving all this closure with union, concatenation, and clean star, we come to the definition of regular expression. So as I said, informally you can say that these are some shorthand notation to express certain languages. So right now it is not immediate that these languages are regular languages. So the goal is to prove that this certain languages within quote unquote is nothing but regular languages, right? So what certain languages, if we do not mention regular languages now? So first of all, we have this notations, this phi, epsilon, and a, where a is some symbol. So if you are so this regular expression should be expression over some alphabet. So you have some symbol, say, in this alphabet, and so this notation, if you use, they are regular expression, and these regular expressions denote some language, right? So there are some notation, and each notation denotes some language. So this denotes the language phi, right? So this is also phi. So what is the difference? If you see the standard textbook, so this will be written in this boldface. Okay, so you will have this boldface here. So boldface here means this is a regular expression. This is just a notation. Okay, and then this will denote the empty set. Similarly, this boldface epsilon, this is not the empty string. Okay, so this is a language. What language? The singleton language, which contains this empty string. So this epsilon without boldface is the empty string. So this is not the empty string, this is the language containing the empty string. Okay, so just keep a note of this differences. Similarly, when we use this boldface version of a symbol, this is not the symbol itself. Okay, so this denotes the singleton set containing that symbol, right? So this is also a language. So each of this expression denotes some language. Okay. So now we can recursively define other regular expressions. So if R and S are some regular expression, and suppose they denote this language capital R and capital S, right? So then we use this plus or just like this concatenation or this clean star over regular expressions. Okay, so these are regular expressions. Yeah. So R plus S will then mean the union of this capital R, capital S. So this concatenation of the regular expressions will be a new regular expression which will denote this language RS and so on, right? So this is, so this part are regular expression, right? So they are just some notation, some expression, and what they mean is these languages. So these are languages, right? So you can have say if you take R to be say phi, S to be say A, so you can have some regular expression like phi plus A. So these are bold case, the bold face, right? So phi plus some bold face A. I don't know how to write it with a pen. So that will be say a regular language. And what will be that? So it will be just union of this thing. So this union this, so it will be again just this, right? So what will be say phi A? So it will be concatenation of these two, and that will be phi, right? So in that sense we can now construct other regular expressions starting with say this basic block. So these are like the atoms, okay, and now we can put this atomic things together with this operators plus and this concatenation and stars, and now can construct complex regular expression, and the language they denote is related like this. And similar to this capital R star, we also use this plus here. This is strictly speaking not part of the definition of regular expression. These are just some syntactic sugar and some extension of this basic definition, you can say. And again, similarly, this Ri is Ri many times. So now when do we say that this R is equal to S? If the language they denote is equal. So if R is a regular expression, the language R is denoting is written as L of R. Okay. So here, for example, this denotes this. Mathematically, we can write it as L of this boldface, whatever this boldface epsilon is the language this. Okay, so this is what we should write to be precise, and we have a equality here if the corresponding languages are equal, right? So one thing I should mention here, that though strictly speaking R and L of R are not the same thing, this is just a notation and this is a language, and strictly speaking we cannot put a equal to here, but we most of the time we do that. So for example, we should say that this what can I say, say a plus b, this boldface A and boldface B. Okay. So I should rigorously say that this L of this is equal to, say, union of this and this, which is AB, right? But often we just say that so often we say that this is actually this thing. So strictly speaking, this equality should not make sense, but we abuse the notation and we interchangeably use the regular expression and the set. So we can do this interchangeably. If you see a regular expression, you can immediately interpret it as the set instead of saying that it denotes the set. Depends on the context. if you want to make a distinction, you can use this capital R notation. Otherwise, it will be understood that L is there and it's invisibly present everywhere. So, for example, we can talk about say this A star, say A star union V star. So this makes sense if you treat them as the set, not just the notation. So this, or even say intersection. So these are not regular expression, you see, because in regular expression there is no intersection. But this still makes sense, because then what you are actually meaning is that the L of this intersection with the L of this. Okay. So in that sense, it's equivalent. So we do that interchangeably. Do not get confused with that. Okay. So some example of regular expression. So what is this thing? This is the concatenation of this set and this set. And what are these sets? So these are just singleton 0, singleton 0. If you take a concatenation, you will get this thing. So it is easy to see that if you just have some concatenation of symbols here, so then the corresponding set will be just the singleton set containing the corresponding string, right? So this looks like a string, and this will be the corresponding singleton set containing the string. So what is this? Again, 0 is just the singleton set 0. 1 will be a singleton set containing 1. So plus means union, right? So this means 0 union 1, that means this, and then the star means star. So this is the set of all strings constructed out of 0 and 1, right? So what is this thing? So now if this is any string of 0 and 1, and if this is any string of 0 and 1, you see that there is a 0 0 setting in between, right? So that means this is the set of all string which contains 0 0 as substring, so which has at least 2 consecutive zeros, right? Now what is this? So I claim that the set of strings here can be expressed like this. So it denotes all strings of 0 and 1s beginning with 1 and not having 2 consecutive zeros, right? So okay, it begins with 1. That is easy to see, because this is 1 and 1 0, and then it's star, right? So you have to start with at one of this thing. So you can start with, say, 1, or you can start with 1 0. So maybe 1 0 1 1 1 0. So it's like you are breaking this into this and this, and maybe again 1 0, maybe again 1, something like this. So strings of this form. So you see it starts with 1, but how can we say that it has no two consecutive zeros? That's because you see that any zero that occurs here in the string. So if that string is in this set, so now we are treating this as the set. So if you have any string in this set, and if you consider any zero in that string, so that string is here because it came from here, right? So that means that string has to have a 1 before this thing. Sorry, that 0 has to have a 1 before it. So any 0 you have here, that must have a 1 before this. So you cannot have a 0 0, right? So if you have, say, a 1 0, you have something, a 1 before this, and also after this you cannot have a 0 because after this either you can have you cannot have this 0, either you can have a 1 0 or you can have a 1. So either way you see that you cannot have a 0 0. So the argument I gave shows that this set of string is contained in this set, but then you can also argue that this thing is contained here. So both ways the containment works. So this is actually equal to this. And if you want to be strict, again I am saying you can use this L of this is equal to this, but then this L is kind of understood. So we treat this itself as a set, right? So similarly, you take some time and try to convince yourself that this actually denotes this strings and this actually denotes this string. Okay, so I'm not going to explain this and this. So you just try to imbibe the definition and all those ideas. Stop for a moment and try to convince yourself that these expressions indeed correspond to this, because these are common sort of questions. So you will be given some plain English description of some language like this: do not have two consecutive zeros, do not have something, and then you will be asked to write a regular expression for that. So it's better to have a habit of constructing a regular expression from a given property. Okay. So these regular expressions have some expected property, and they are easy and boring to prove, but they are important because it's like this looks like a algebra, right? So it's like the class, this is like the multiplication, and you see that this plus is actually commutative, right? And it is showing that this plus is associative. This is showing that this concatenation is associative, and this is showing that this concatenation is distributive over this plus. So all these algebraic relationships are very useful when you are trying to convert one regular expression to another. And similarly, so this is true for in both ways, and these are again useful identities. So this is useful. In fact, many of these identities, in fact almost all of these identities, you can prove for arbitrary language if you think in terms of language. So what is it saying in terms of language? Say this A is saying that R union S is equal to S union R, right? And this identity holds irrespective of the fact whether this R and S are regular language, whether they can be expressed by a regular expression or not. So they hold for arbitrary sets, right? Not even for oh, here we're talking about sets of string, because concatenation only makes sense with a set of strings. So, but with any language, you can try to prove the language version of these things. For example, for any language R, we define this clean star, and then you can try to prove that if you take the stars twice, then this is equal to this, right? This is kind of understandable, because what you have here is that means you are taking multiple strings of this thing and concatenating them. So you are taking something multiple times, and each of this are coming from, say, R star, and you are concatenating them, but each of them are coming from R star, means they are again kind of concatenation of strings which are coming from, say, R, right? So each of this thing is coming from R, some string here, right? So all this brackets means there is some string here from R. So then again, this whole thing will be in R star, right? So so you can just try to write formally induction depending on the string length. What string? So if you are trying to prove something, some L1 is equal to L2, so you have to prove that x belongs to L1 if and only if x belongs to L2. So you first prove, say, this, and then you prove this, and that you do with the induction on the length of x. So these are trivial examples, but these are important identities. Okay. So what we said in the beginning of the lecture, that our goal is to show that these regular expressions are exactly equivalent to this regular language. So that means this, if you have any regular expression R, then LR is a regular language, and the vice versa, but that we will show later. That if you have any L, so then you can construct a R so that this L is actually L of R. But here we are proving that for given any regular expression R, so this LR is regular language. So this is the thing, that this is the one direction that we are proving right now. So again we have induction, and what is the induction parameter? So it is the number of operators in this regular expression R. So R is a regular expression, right? So that means it's constructed out of either this phi epsilon, or this capital, this boldface A for some symbol A, and then you can add this plus and concatenation and clean closure. So these are the three operations you can apply repeatedly. Okay. So to construct this thing, and we are doing the induction on the number of these operators. So what is the base case? That your regular expression, whatever you have, has zero many operators. So zero many operators means you can have either this or this. So they do not contain any plus, star, or concatenation. And for each of this, you can construct automata, a finite automata, right? So this is this just accepts empty string. You see, it doesn't accept anything else. So this does not accept anything at all, not even epsilon, because there is no path, and this just accepts A, right? So these are automatas for this regular expression. So these are regular. Now what is the induction step? So now you take some arbitrary regular expression R, and your induction hypothesis is that whatever operators are present here, so for all regular expressions which has fewer operators, for that this holds, right? So that means if you have some S and T which contains fewer operators than R, then by induction hypothesis for S and T we have that this L of S and L of T are regular languages. But then this R, what this R can be, right? So by definition this is either class of two regular expression or concatenation of two regular expression or clean closure of some regular expression, right? And in each of this case this S and T will have fewer operators than R, right? So just if you see this example, right? So if this is your R, right? So you can break it down as, say, this as your S, right? And then this as your T, and then each will have fewer operators. Again you can break this up into this and this star. You can break this up into this concatenated this. You can break this with star. So you can do this induction on number of operators, right? And the induction goes through. And how do you argue that this L of R is regular then? Because we have already proved that if this is regular and this is regular, then this union is regular, this concatenation is regular, and this clean star is regular. So this is where we require those closure property of regular languages, right? So this is telling you that L of R is either this or this or this, and the closure properties are telling you that so the induction hypothesis is telling you that each of this is regular, and the closure properties are telling you that if you combine it with union, concatenation, or star, so then that is also regular. So the induction goes through and you see that L of R is actually a regular language. So this part is fairly easy once you have the closure of union, concatenation, and a clean star in regular language. So this is kind of immediate and you can see this immediately. So now you have a mechanism to convert a regular expression into a finite automata, right? So given a regular expression, you need to break it down into smaller regular expression. So how do you break this down? So so you take this and this, right? So you break it down into concatenation of 0, 1, star, then 1, and then 0, 1, right? So if you construct machine for this and then this, then you can take the concatenation like we did in this proof, right? So if you have a machine for this and this, then you can just put a epsilon transition here. So this is what is happening here. So this entire thing is for this part, okay? Then we have just this one which is for this part, and then we have here to here which is for this part. And then again, how are we constructing this thing or this thing? So this is the union of 0 and 1, right? So again we are using this construction. So if you have a machine for this and this, then we are using this epsilon transition. So here in this example, we have a machine for 0 and 1, which is just this 0 and 1. So this is the machine for 0, this is the machine for 1, and you see that we are just adding this epsilon transition. So this whole thing becomes the epsilon machine for 0 plus 1. And now you see, if you have this machine, okay, so you exclude this arrow. So if you are just considering, say, this and this thing, so this is again just 0 plus 1, and then you are doing a star. How again? So this was the construction, right? So you use this epsilon transition and then this backage, and with this and this. So it's the same thing. So this part is just 0 1. So we are using this here. We are using this backage and this and this. So this entire thing then becomes the automata for 0 plus 1 star. So in this way, I'm given a regular expression. You can break it down according to the operator, and using those graphical construction techniques, you can construct a finite automata for that. So this will be a epsilon NFA. So you can convert this to NFA without epsilon transition. So that will introduce many more edges. And then if you like, you can convert that to a DFA, but then you saw that the number of state will be exponential, right? I mean, if your original number of state is n, then the number of state will be 2 to the n, right? So in that sense, there is an algorithm, but it will give you a horribly complex looking DFA. So if you are asked to construct, say, a DFA which is equivalent to a regular expression, you have to be clever, and you have to see what the property of the strings are. So you have to make this shortcut in your head. I mean, you cannot just blindly follow these algorithms. But nonetheless, this theoretically proves that they are all equivalent, right? Not equivalent. So we haven't proved the other thing, but at least we showed that if you have a regular expression, then you have a corresponding finite automata. So the next thing is to show that if you have a finite automata, then you have a regular expression corresponding to the same language. I'm denoting the same language, right? So let's go to that proof now.